Okay, so the next thing that we have here is called basically compound statements. And of course these are simple things, but they have probably a big name. Although the name is not that big either, but they are basically part and parcel of mathematical logic and reasoning, of course. So many mathematical statements are obtained by combining one or more statements using some connecting words like and, or, etc. Consider the following statement. There is something wrong with the bulb or with the wiring. So the statement is P. There is something wrong with the bulb or the wiring. So there is an or over here. Now this statement tells us that there is something wrong with the bulb or there is something wrong with the wiring. So if you want to break this down, you can say that there is something wrong with the bulb or there is something wrong with the wiring. That means that basically this statement is actually made up of two smaller statements, meaning that you can write this statement as two smaller statements as Q. There is something wrong. There is something wrong with the bulb. And there is another statement, there is something wrong. There is something wrong with the wiring. Which basically there is these two statements Q and R that are connected by or, right? Now suppose two statements are given as, for example, P and Q. Now suppose two statements are given as by P and Q as 7 is an odd number. Statement P is 7 is an odd number, and statement Q is 7 is a prime number. 7 is a prime number. Now these two statements can be combined with an and, meaning that instead of these two you can write R as 7 is both odd and prime number. 7 is both an odd and prime number. So now basically over here we have used the connecting word and in order to connect these two statements. So this statement R, we call it a compound statement because it's basically the basically two statements put together using connected with a word like for example and or some other connecting word, which leads us to the following definition as definition number 2. Definition number 2, which is a compound statement, is a statement which is made up of two or more statements. In this case, each statement is called a component statement. So a compound statement is a statement which is made up of two or more statements. Which is made up of two or more statements. In this case, each statement is called a component statement. A component statement. So that's basically the definition of a compound statement. So a compound statement is a statement which is made up of two or more statements. And in this case, each statement is called a component statement. Now we have a couple of examples here. So let's see what these examples are. So example number 4, you want to find the component statements of the following compound statements. Finding the component statements of these compound statements. For example, the sky is blue and the grass is green. The sky is blue and the grass is green. So the component statements are the sky is blue. If you take this as, for example, give it some name, for example, R, then the components, if you take the components as P and Q, basically you can write P as the sky is blue and Q, you can write it as the grass is green. With the connecting word and. The connecting word is and. Number 2, it is raining and it is cold. Let's say that your R is, for example, it is raining and it is cold. So then your P, for example, would be it is raining, and your Q would be it is cold. So the component statements are these two, P and Q. They are connected with an and. As another example, let's say you have all rational numbers are real and all real numbers are complex. So your R, for example, is all rational numbers are real and all real numbers are complex. So the component statements of this compound statement would be all rational numbers are real, all rational numbers are real, and Q and all real numbers are complex. All real numbers are complex. And these two component statements are connected using an AND. Number 5, 0 is a positive number. Take your R for example as 0 is a positive number. And a negative number. Or a negative number. So the component statements of this compound statement are basically P. 0 is a positive number. And Q, 0 is a negative number. Zero is a negative number, and the two components are connected together using the word OR. Now the next question is find the component statements of these statements and check whether they are true or not. For example, statement number 1, or let's call it for example R, a square is a quadrilateral. A square is a quadrilateral and its four sides equal, and its four sides equal. So the component statements are P, a square is a quadrilateral, a square is a quadrilateral, and Q, a square has all its sides equal. A square has all its sides equal. So we know that a square is a quadrilateral, and of course a square has all its sides equal. So then we know that both of these statements are true. And here the connecting word is AND. right? And both of the statements are true. Number 2 is all prime numbers are either even or odd. For example, R is all prime numbers. All prime numbers are either even or odd. All prime numbers are either even or odd. So the component statements would be basically the all prime numbers are odd numbers. All prime numbers are odd numbers, and Q would be all prime numbers. All prime numbers are even numbers. Now, all prime numbers are odd numbers is of course false, and all prime numbers are even numbers are of course false as well. So both of these statements are false, and the connecting word is or. Okay. Number 3, a person who has taken mathematics or computer science can go for MCA. So for example, let's say that you have a statement, a person who has taken mathematics or computer science, mathematics or computer science can go for MCA. MCA is a course in India which is Master of Computer Application. Okay. So it says that the person who has taken mathematics or computer science can go for MCA. So the components are P, a person who has taken mathematics can go for MCA. And Q, a person who has taken computer science can go for MCA. And both of these statements are of course true, and the connecting word here is or. So in the example that we had before, both of these statements were false and they were connected with or. Over here, both of these statements are true and they are connected with or. So that's basically one thing that you can pay attention to. Now, another statement that we have Chandigarh is the capital of Haryana and Uttar Pradesh. So Chandigarh is the name of of course it's the name of the capital of Haryana and Uttar Pradesh, 2 states in India. Is the capital of Haryana and Uttar Pradesh. So this is your statement. So the component statements here are basically P. Chandigarh is the capital of Haryana, and Chandigarh is the capital of Uttar Pradesh, right? So Chandigarh is the capital of Haryana, that is true, and Chandigarh is the capital of Uttar Pradesh, that is also true. So they are basically both of these statements are true, and they are connected with an and. So the first statement is true. I'm sorry. So this is not true. Okay, this is not true. So the first statement is true, but the second is false. Here the connecting word is and. And here the connecting word is and. So I suppose that this statement over here would be false, of course. The next statement that we have is square root of 2 is a rational number or an irrational number. Is a rational number or an irrational number. So square root of 2 is a rational number or an irrational number. Let's take this as statement R. So the component statements here are P. Square root of 2 is a rational number. Is a rational number. And Q, square root of 2 is an irrational number. So of course you know that this statement is false and this statement is true. And the connecting word here is or. So I suppose now the statement is actually true over here. But we are still probably not talking about the validity of these statements when you use these connecting words. But you can of course pay attention to them at this stage as well. Now, the next question, the next statement that we have is 24 is a multiple of 2, 4, and 8. R is 24 is a multiple of 2, 4, and 8. And over here you need to pay attention to the fact that when you say 24 is a multiple of 2, 4, and 8, that means that there is an and over here as well. So we don't write it, but we write it 2, 4, and 8. So that's basically implied. So the component statements are, for example, S, R, and T. S, or if I call this P, for example, I can call these statements P, for example, Q, and R, and I can call this statement S. So then you can say that 24 is a multiple of 2. 24 is a multiple of 4. 24 is a multiple of 8. So that is that. So these statements, this is true, and this is true, and they are all connected with the word and. We observe that compound statements are actually made up of 2 or more statements connected by words like and, or, etc. These words have special meaning in mathematics. We shall discuss this matter in the following section. This is of course very important because the words, these connecting words, and we have or, and we have some other such words that we use in order to connect these statements together. These words have specific meanings and definitions in mathematics. It's not like the way that you use them in day-to-day, basically our daily language. It's not like that. And I suppose, I mean, if it was up to me, I would have discussed this, for example, in the beginning of at least class 7, because from class 7, all of this business of and or practically starts in the text. But you get, I mean, in many places, at least in these books, I've gone through all of these books. You get confused. You don't know what is meant by the statement, because normally you understand the meaning of the word based on the English language, but the meaning of the word is not basically what you would know based on the English language. So you need to basically know the definitions. So that's basically that. So anyway, in the next section we will basically we will talk about the meaning of these words and phrases. But before that, we have a couple of exercises that we will go through in the next video. See you in the next video. Or let's do that over here, because there is still time in this video and I don't want to lose this time. So exercise 14.2. Exercise 14.2. So we want to basically, question number 1 is write the negation of these statements. So if you want to write the negation of a statement, for example, let's say the statement is Chennai is Chennai is the capital of Tamil Nadu. Is the capital of Tamil Nadu. So Chennai is the capital of Tamil Nadu. The negation of this would be it is false. For example, you could say it is false that Chennai is the capital of Tamil Nadu, or you can say that it is not the case that Chennai is the capital of Tamil Nadu. So you can say, for example, it is false that Chennai is the capital of Tamil Nadu. And this statement can be written as Chennai is not the capital of Tamil Nadu. Okay. So this kind of statement is easy, and there is not much confusion about that, but we will get to more complicated statements as well. So part 2 of this question is square root of 2 is not a complex number. Square root of 2 is not a complex number. So when you say square root of 2 is not a complex number, the negation of that, you could say it is not the case, for example, that square root of 2 is not a complex number. So you would say square root of 2 is a complex number. Square root of 2 is a complex number. And of course, you can see that square root of 2 is not a complex number is of course false. This is a false statement, because every real number is basically a complex number. But now the negation of this statement becomes this statement here, which is square root of 2 is a complex number, and square root of 2 is a complex number, and the negation is of course true. So when you have what it means is that when you have a statement, for example, suppose that your statement is false, when you basically make the negation of that statement, the negation of that statement is true. Okay, so that is that. And part 2 is square root of 2 is a complex number. Okay, so part 3 of this question says that all triangles are not equilateral triangles. Of course, the sentence is kind of wrong. I mean, as far as the English language is concerned, not written in the best way possible, but it says that all triangles are not equilateral triangles. Are not equilateral triangles. It's written this way, are not equilateral triangles, which is not the best way of writing this statement. It's written all triangles are not equilateral triangle. So what this statement actually means is basically, if you were to rewrite this statement, is that not all triangles are equilateral triangles. You can write it this way. What that means is this: not all triangles are equilateral triangles. Not all triangles are equilateral triangles. And what that again, if you were to rewrite this statement here, this one, you would write it as there is at least one triangle. There is at least one triangle that is not an equilateral triangle. That is not an equilateral triangle. There is at least one triangle that is not an equilateral triangle. Okay. So now the negation of this statement is that you could say basically the negation of this statement, you could say that it is not the case. It is not the case that there is at least one triangle that is not an equilateral triangle. That is not an equilateral triangle. So the statement, the negation of this statement is, it is not the case, okay, that there is at least one triangle that is not an equilateral triangle. There is at least one triangle that is not an equilateral triangle, meaning that it's some other sort of triangle. That there is at least one triangle. So what that means is that then when you say that it is not the case that there is at least one triangle that is not an equilateral triangle, the negation of that means that there is no triangle that is not an equilateral triangle. That means that all triangles are equilateral triangles, which brings us to the negation that all triangles are equilateral triangles. And if you compare these two statements together, over here we say all triangles are not equilateral triangles, and over here we say all triangles are equilateral triangles. But again, basically what you have from here all the way up to here, you need to understand them. Otherwise you might make sense of this sentence in a wrong way. So number 3 is all triangles are equilateral triangles, and basically these are important because when you want to phrase your sentences, you have to phrase them in this in at least in mathematics. In day-to-day language, people usually don't do this kind of thing. And usually the kind of logic that people use is basically, when it comes to day-to-day language and basically what's going on between people, it is that basically people use logic. Basically people use logic in order to get their own way, meaning that it doesn't really matter to them whether what they're saying is logically correct or not, what they're saying is true or not, what they're saying is actually right or not. They don't care about this, usually, most of the time. What they care about is that they use logic in such a way that they get their own way, meaning that they get what they want. That's basically what we human beings do. So, but scientists and of course mathematicians don't do that kind of thing, at least when it comes to mathematics. For example, if you want to build a rocket and send that rocket to space, it doesn't really matter whether I think, for example, the rocket is beautiful or not, or it's nice or not, or it's very well finished, or the color is very beautiful. That doesn't really matter. That's my personal opinion. It doesn't really matter. What matters is that the rocket is technically fit so that when it goes to outer space, it can do whatever it is supposed to do. It needs to be able to go over there. It needs to be able to, I don't know, fly, go to outer space, do all of the, basically finish its mission, and probably come back if it's supposed to come back. So, over here, when it comes to mathematics and physics, for example, my personal opinion, whether or not I get my own way, whether or not my feelings are hurt, whether or not, for example, whether or not people think that I'm a good person or a bad person, those kinds of things are not important, are just simply immaterial. What's important is that basically the statement that I make is logically fit and logically sane based on the logic of mathematics. And that's basically what we do in mathematics. So then, again, when you read these kinds of statements in mathematics, you need to be able to just simply understand the meaning of them, at least in the context of mathematics. And in your day-to-day life, it's up to you how you want to lead your life. That's another matter. So the next statement that we have is the number 2 is greater than 7. The number 2, the number 2 is greater than 7. So the negation of this is a simple statement, and it's not hard to understand it. So the negation of this would be, it is not the case. It is not the case that basically that the number 2, that this whole thing comes over here. it is not the case that the number 2 is greater than 7. That means that you can rewrite this as the number 2 is not greater than 7. So number 4 is the number 2 is not greater than 7. And number 5, it says that every natural number is an integer. Every natural number is an integer. So when you say every natural number is an integer, that means that there is no natural number that is not an integer. Now the negation of this you could say that not, for example, you could say not all natural numbers are integers, or you could say that I would call it this way, or you could say there is at least one natural number that is not an integer. That is not an integer. So number 5 is but they have written it as every natural number is not an integer, and I suppose well, we can let that slip, but really, if you want to write it right, to write it properly, you have to write it this way. Now, question number 2 is, are the following pairs of statements negations of each other? So, you have one statement here, the number x is not a rational number. We have the number x is not a rational number. Is not a rational number, and then the negation of that is the number x is not an irrational number. Is not an irrational number. So the statement is the number x is not a rational number, and the negation is the number x is not an irrational number. So when I say the number x is not a rational number, so what that means is that, well, it's simply x is not a rational number. So when it's not a rational number, of course it could be an irrational number. So this is not the negation of this statement is not, of course, the right negation of this statement. And if you want to negate this statement, you would say the number x is a rational number, for example. Is a rational number, for example. So the negation of the first statement is the number x is a rational number, which is the same as the second statement. This is because when a number is not irrational, it is rational. Well, let me see. The number x is not a rational number, so it is an irrational number. Oh, okay. So so it says that the negation of the first statement is the number x is a rational number. So if you want to negate this statement, you would say the number x is a rational number. Is a rational number. Is a rational number, right? And this seems to be the same thing as the second statement, because when a number is not a rational, when a number is not an irrational number, it is a rational number. So the meaning of this sentence is the number x is not an irrational number, which means a rational number. A rational number. And as you can see, these statements, the number x is a rational number, the number x is a rational number, they are the same. That means that this is the negation of this one. So you need to be careful over here. And number 2 is the number x is a rational number. The statement that you have is the number x is a rational number. Is a rational number. And the negation that has been written for it is the number x is an irrational number. The number x is an irrational number. So the negation of this would be the number x. You could say it is not the case that the number x is a rational number, so it has to be an irrational number. So the number x is an irrational number is the negation of that. So number 2, the answer that we have in the book, it says the negation of the first statement is x is an irrational number, which is the same as the second statement. Therefore, the pairs are negations of each other. Now, question number 3 is find the component statements of the following compound statements and check whether they are true or false. So the component statements of, for example, number 3 is prime or it is odd. Number 3 is prime. Number 3 is prime or it is odd, right? So the component statements of this compound statement are number 3 is, so there has to be an is over here. Number 3 is prime, and the next component is number 3 is odd. Number 3 is odd. And they are connected together using OR. Now, number 3, of course, is a prime number. That is true. And number 3 is odd. That is also true. The answer over here, number 3 is prime, number 3 is odd, both are true. The second statement that we have here is all integers are positive or negative. All integers are positive or negative. So the component statements here are all integers are positive all integers are negative. All integers are negative. So all integers are positive is of course false. There is at least one integer that is not positive. All integers are negative is false because there is at least one integer that is not negative. So both are false, and they are connected together with an OR. So all integers are positive, all integers are negative, and false. And the third part of this question is 100 is divisible by 3, 11, and 55. 100 is divisible by 3, 11, and 5. So that the component statements of this compound statement are 100 is divisible by 3. 100 is divisible by 11, and 100 is divisible by 5. This is false, this is false, this is false, this is true. This one is true, and they are connected by AND basically. So the question is, check whether they are true or false. Find the component statements of the following compound statements and check whether they are true or false. And the problem over here is that it says, for example, 100 is divisible by 3, 100 is divisible by 11, and 100 is divisible by 5. And there is only one false over here. I don't really know how to make sense of that false, what that refers to, but we will see about that. I know that basically individually 100 is, of course, 100 is divisible by 3 is a false statement. 100 is divisible by 11 is a false statement. This is a true statement. Now, how the whole thing becomes false, if that is at all the case, then we will see about that in the next video. So you don't need to really worry about this, because I have come across some sort of conflicting logic regarding the definition of true and false in the first place. So we'll have to see about that, but let's see how that goes. In the next section, hopefully we will get over that problem. So I'll see you in the next video.